Welcome to Brain Vision.
We're told a sled is given a kick on a frozen pond. The kick imparts to the sled initial velocity v, or initial speed v. We have a coefficient of kinetic friction between the sled and the ice is mu k. I guess I've just called it mu here. I want to use energy considerations to find the distance the sled moves before it stops. Okay, so we have our sled here, and in the horizontal direction, we just have this frictional drag force here. And the frictional drag force is mu times the normal force acting on the sled, which would be out of the surface here. And that's mg. So the frictional force is going to be mu mg. The non-conservative work that force does is that the distance over that force times the distance over which it acts. This force is constant, so that's why we can actually, the power is F d dot, but when we integrate that to get the work, F is constant, so that's just the work is the non-conservative for work is just F times d. So that means it's mu mg times d, the distance that over which that force is acted. Now, initially, the sled has a velocity v, so it has some initial kinetic energy, which is 1/2 mv squared. V squared. So then we want to figure out when the sled stops, and at that point, then the kinetic energy is 0, and that the kinetic energy is going to be, there's no change in gravitational potential, so we'll just use the gravitational potential that it has throughout the problem as 0 as the reference. So we have no kinetic gravitational potential in here. So the total energy at the end, when the sled comes to rest, is 0. So we know that when the non-conservative work must be equal to this initial kinetic energy. Basically, this is saying that this is the energy the mechanical energy that gets dissipated must be equal to the initial kinetic energy. And so equating those things, we can see that m drops out, and we get that d is simply v squared over 2 mu g. So again, we can see that g comes to play here. As mu increases, d decreases. As v increases, d increases. What did I say? As mu decreases, d increases. As v increases, d increases, which all makes sense, right? So when you derive these equations using variables, it's always good to make sure that these what you get here makes sense. And it makes sense that you kick it harder and it's going faster, it's going to go farther. It also makes sense that if the drag or if the coefficient of friction is greater, it's going to go not as far. It's not going to go as far if you give it the same kick. So this all makes sense. Units all work out too. So again, this is the answer.